robotics platform, and our demo has been successfully shown in October Festival. So,
Okay.
Yeah, let's welcome Eric.
Okay, so good afternoon, everyone. So today I'm going to present my work in media for the past 4 months as a robotics engineering intern. And my contribution is the motion control of the intelligent robotic platform. So the main application for this platform is a physical therapy robot. And let me show you the final result of the robot. So this platform consists of 3 parts: the motion control, force control, and voice control. So the user can give the robot some basic commands for the robot to move accordingly, such as start, pause. And you can see it's very stable and reliable. We have tested multiple times, and the tragedy never happens. The user can tell the robot to press harder. Is that okay? And also can tell the robot to press louder. And also can tell the robot to stop in Chinese. Okay, so my contributions for my internship is mainly these 4 parts: motion control, force control, therapy motion patterns design, and hardware design and fabrication. So the reason why we want to build an intelligent robotics platform is because nowadays our world is undergoing an evolutionary change. So we are calling for intelligent manufacturing and robotics. And therefore for media, both for future product development and industrial manufacturing, a comprehensive intelligent robotics platform, which is capable for medical care and industry service, is very important and necessary. And for robotics platforms, the motion control is one of the most important components. So the development framework for this platform is like this. So this is a big picture of the framework. It mainly consists of 3 parts: the control package, where is mainly written in Python and C++. And this is where I spend most of my time on the work. And the ROS, which is an open source robotics operating system built on top of the Ubuntu Linux, and also the physical robot. So the ROS is in charge of the communication between the software control package and the robot. And the control package can send control commands to ROS, and ROS will convert this into control signal to the actual robot. And the robot will give feedback to the ROS, and ROS will talk to the control package. So this is the environment and the ecosystem. The first part of my contribution is motion control. So for any industry task, such as picking a thing and move this object to another place, for robot, can be converted into the issue of control in workspace, and also can be converted to an issue in configuration space. The workspace means it's normally a 3-dimensional Cartesian coordinate where the robot's any effector can reach. And the configuration space is also known as the joint space for the robotic arm. And it depends on the dimension, the degree of, and its dimension depends on the degrees of freedom of the robot. And also take notice, there is also a transformation between workspace and configuration space. The main challenge for the motion control in workspace or configuration space is how can we generate the intermediate points between the beginning point and the goal points. So this is known as how to generate the waypoints of the motion trajectory in the robotics workspace or in its configuration space. And I have proposed the three solutions. The first one is I have used linear interpolation or high-dimensional polynomial interpolation to interpolate the intermediate points between the start point and goal point. The second solution I implemented is the conventional sampling-based path planning algorithms in the OMPL in movie, such as RRT star, and PRN. The last method I implemented is called DMP, this dynamic movement primitives, and I will give more details about this method. And this algorithm is published into ICRA 2009. Okay, so regarding to my slides, do you have any questions?
How many joints does the robotic arm have?
For our robot arm, we have 7.
7.
Yeah, so the degree of freedom is 7.
So you have the control. You have 7 actuators also.
Yeah. So the actuator is the electric motor, servo motor inside the robot. That is the low level side, and we mainly works on the high level side, where we can talk to the low level to control it.
Okay.
Yeah.
The three solutions are working together, or just one is working?
The three are all working, but they have different. Maybe for different scenarios, we have some methods better than others. So for linear, this method is the most simple one, is the simplest one. The second one, there are lots of algorithms, but these are all called sampling-based path planning. It's very normal in academic and also industry, but it's pretty useful and much more complicated. The last one is I personally researched about this and found this is very relevant to our scenario. So I also tried the third one. So all these three methods are working.
In all those solutions, do you aim to achieve the optimal control, or you just try to achieve a good control, good path?
It's not. These methods are not guaranteed to have the optimal solution. For example, the sampling-based path planning, it can just give you a workable solution, but this may not be the optimal one. But for our scenario, because we want to build a physical therapy robot, so it does not have to be the most optimal configuration.
Right.
As long as it can achieve our target, fulfill our requirements, that is fine. Yeah. And there's also another method. It's called optimization-based path planning. For that one, it is computationally much more intensive, but it will guarantee we can generate the optimal solution. So talking about the DMP, so the basic idea of DMP is we can use a group of differential equations to describe a system. And this system mainly contains of two parts. The first part is attractor dynamics, which means the system will converge to its goal states in the steady state, and also a nonlinear force term. And this force term is to mimic the target force term. The force term can be very high dimensional and highly nonlinear. So the DMP algorithm is to learn the weight, to learn this nonlinear force term. And this nonlinear force term is a combination of Gaussian basis functions. And the Gaussian basis functions has a group of weights. So the learning target is to learn what is the best optimal combination of the weights for the Gaussian basis function to mimic the target nonlinear function. So with this mathematics properties, this method will generate a human-like movements. So the movements can be very smooth, very high dimensional, and very highly nonlinear, and very complex movements.
Why Gaussian here? Not anything else?
Pardon?
Why Gaussian? Why you choose Gaussian?
This is proposed in the paper.
Okay.
Yeah, because you can, the combination of Gaussian basis is here. The I is the number of Gaussians you choose,
right.
And you can customize this in the program. And for my case, I use 10 Gaussians. If you have a very highly nonlinear movement, you can increase the I, so the computational time will be increased.
There must be some rationale behind it. Right?
Yeah, yes, right. Because for a distribution, if you have a random distribution, which is not Bernoulli or Gaussian distribution, but you can combine a mixture of Gaussians to mimic that distribution. So the distribution, in the mirror of the distribution is also the shape of the nonlinear, between the output and the input. So it's a transformation. So you can also use a group of Gaussians to represent that nonlinear transformation between input to output. So yeah, so it is this term.
Excuse me.
Yeah.
The f is s function of s, but differential equations nothing to do with.
Pardon?
I mean the function f is a function of s,
Yeah, that's right.
and
Ah.
differential equation does not have.
Does not have S.
Yeah.
Yeah. So if you want to know more details, I can tell you.
I just
So
curious.
yeah, the S is a phase term.
Phase.
Yeah. So they normally this method they convert the time t to the phase S.
Okay.
So I think it's because of it's more mathematical, easier to calculate. So they transform the time into a phase. So the range of the S is from 0 to 1. So all this term actually has something to do with the time.
Okay.
Yeah.
Otherwise, it becomes constants in the equation.
Yeah, that's right. That's right.
Okay.
Because there's lots of intermediate process I didn't put it. Okay, so let me introduce step by step how to carry out this DIP method. So the first step is the robot is guided by a human engineer to do the highly nonlinear movement. In this case, I teach the robot to do this. I take notice that the demonstration data collection procedure is not the same as the neural network. Yeah. So the demonstration data collection procedure is not like our neural network training process, where we have feed tons of data into the system to let the system to know about this nonlinear transformation. But this one, we just need to collect one group of data. So it's called a demonstration data collection.
Maybe you can play the video again.
Yeah.
But this is something new.
So yeah, the robot is guided by a human engineer to do the movement. The robot want to learn. Yeah, you can, for example, I can move the robotic arm in this way, in some other nonlinear, smooth way. Yeah. So
So
this
you
is,
can train by touching it and moving it.
yeah, so this is a data collection procedure. The second step of the DMP is the user or the human engineer can customize a new initial state and a new goal state for the robotic arm. Because in my case, I want the robot to learn a very complicated movement where it's acting like a human being. So I give this initial state and goal state in its configuration space rather than in its workspace. So the robot will know how to generate those drawing states in between. The last step is the final step is where the DIP algorithm generates a plan for the robot and lets the robot to move accordingly from the new initial point to the new goal point, and also retain the characteristic of the demonstration movement. Yes, so this is a movement learned from the demonstration. The last part of the motion control is the transformation between workspace representation and the configuration space representation. On the left-hand side, the waypoints is in its workspace. On the right-hand side is the low-level side, which is the servo motor position or speed. It is in its configuration space. So by inverse kinematics, we can transfer the data from waypoint from its workspace to its configuration space. And we can transfer from its configuration space state back to the workspace state using forward kinematics. So these are some commonly used academic, commonly used in our industry, commonly used method. The second part of my contributions in my internship is the force control. So the challenge of force control is how do we exert a normal force to a surface or to the patient with a suitable magnitude. So my solution is integrate the sensors and feedback control. There are two modes to achieve this target. The first mode is I make use of an external tactile sensors as a feedback for the motion control, for the force control. The advantage of this method is it is compatible with any robotic arm, because we can always put an external sensor to the object we want to serve. So the bottom diagram shows the closed loop of this force control. Here we have a reference force. This is the desired force we want to exert to the patient. And we also have the readings from the tactile sensor. By comparing these two terms, we can find the errors. And we feed this error into the controller. The controller can be PID controller or incremental controller or any other controllers. And this controller will generate the displacement to the end effector of the robot. So the end effector will move accordingly, and the readings of the tactile sensor will also change accordingly. And this whole loop will run on and on in a very high frequency until the difference between reference force and the readings becomes very small.
I'm sorry. What is the goal?
The goal is we want to move the end effector of the robotic arm to exert a certain force to a surface. Yeah, so like I have shown.
Body movement, for example. If you're doing a physical therapy and if your body reacts back because of force, it just.
Yeah, so for the massage, like the physical therapy robot, if you want to exert 50 newtons force onto the patient, how do you control the magnitude of the force? Yeah, so this is just a simple feedback loop. Another mode of force control is I have used the internal torque sensor with forward dynamics. So the mechanism behind it is pretty similar to the previous one. The only difference is we substitute the external tactile sensor with internal torque sensor readings and calculate it by forward dynamics to calculate the force of the end effector. Okay, the third part of my contribution is the therapy motion pattern design. The first pattern I designed is a press. Let's see the result. So this is just a naive normal press at a certain acupuncture spots with a certain force. The second pattern I have designed is a high frequency vibration. So this is achieved by alternating between two lower arm configurations in a very high frequency. So a rapid periodic massage pattern can be generated. So this is also the one used in the first video. Yeah. Last pattern I have designed is a circular rubbing. It's like a human massager doing like this. So keeps the end effector fixed at a certain point, but the wrist is rotating. And this can be achieved by using high dimensional interpolation or the DMP algorithm. And I have tried both of them. The DMP actually works better than the high dimensional interpolation. The last part of my contribution is the massage head design. I basically use wooden piers and magnets to design a pool of different types of massage head. And it can be easily removed and easily installed. So it makes the change process very easy. And also once it's installed, it can be very strong. Okay, so this summarizes my contributions: motion control, force control, therapy motion patterns design, and hardware design and fabrication. And these are my references. Yeah, thanks for listening. Okay, so do you have any questions regarding the materials?
How does it locate different part of the body?
That's for vision part, pure vision part. We have
Yeah.
3D camera to reconstruct the 3D human body and localize the acupuncture points.
Oh,
Also-
so they work together.
Yeah, so it's basically we two work together. And Yuan is in charge of the vision part, and I'm in charge of the control. Given the point, how to move to that point, and how to exert certain force at that point.
The DM, like the method, the DMP will help you to calculate the angles of the.
Yeah, everything. It's the full state. For example, my training procedure was a data collection procedure. Actually take down all the joint positions and the joint speed when I get the robot to do such movement. So after the DMP process all this data, it will give out a sequence of joint positions. Because we have 7 joints, so all those data is a vector of 7, a vector of 7-dimensional. Yeah. So the robot will move accordingly to that sequence of output vectors accordingly to generalize this complex nonlinear movement.
So when it tries to learn the angles, does it like take samples every second or?
Yeah. You can specify that. Right now I specify as 0.5 seconds per second per sample. So it only takes around 20 samples. So if you want to record the movement in more details, you can increase this number. It's all customized.
In this experiment, how to measure the position of each joints and also the angles?
Oh, that is actually realized by this ecosystem.
Okay.
So this is where the robotics operating system comes. Because there is lots of ROS topic you can write, and there are lots of message passed by those topics.
Okay.
And my control package just subscribe to those topics, so I can know about the sensor readings. Yeah, so for the joint positions, it's also the sensors for individual motors. So I just keep track of those positions, and I will know about this data.
So when a new patient comes to the table, does it can automatically measure, or it needs scan the whole body to get a sample? So for example,
Yeah.
like it applies to a new patient,
Yeah.
any requisites things need to do?
Yeah, that's a good question. We are working on that. Yeah, because I think that's mainly in the vision part, where the model can learn from the patient's body size or body shape and locate where are the acupuncture points. Yeah, but my side is more about.
You play the full video or? No,
No, just the control part.
just the control.
Do you want to see? Yeah.
We have a AI learning algorithm here. Because people have different shape, different height, right? And
even the symmetrical.
right. So for a new patient, we will learn a perfect 3D model for that human.
Okay, I think that's our future goal.
Yeah.
If this product is still gonna happen.
No, but thank
Like
you.
it's not.
I just want to let a couple of points is, this project, when we showed up in the AI core, which is in the third fest, there are very few projects. The founder was going around, I want to say this because usually when our founder walks on, he goes direct, he don't stop anywhere. They walk through him through all the projects straight through. There are few steps he stopped and looked back couple of times is only this project. Which means it's he is interested in it. And we are also pushing some of these projects to our AWB 2019, if potentially possible, with our Media Robotics company. Because Media Robotics company works with other vendors and other robotic company, not only KUKA, there are other things we own. So potentially there is an opportunity that if they select, this could go into AWB 2019.
That's cool.
We'll keep you posted.
Yeah, very glad to hear that.
Yeah,
Yeah.
thank you. A lot of work, but it has good vibe in our Oktoberfest, both with MRC and Jimmy, all the.
That's cool.
Yeah,
Yeah.
thank you.
Thank you. Thank you, everyone.